last time we got into measurements and we got into scientific notation. Remember again, when we write a number in scientific notation, n times 10 to the n, that is again a number between 1 and 10. It again is either a positive or negative number, depending on which way you need to move it. You get yourself to a number between 1 and 10. Remember that whenever you write a number in scientific notation, all of those numbers that come before the times 10 part are always significant figures. And that means, as we talked about, there are sometimes only one way to give an answer to the proper number of significant figures, and that is to write it in scientific notation. There is sometimes just no way to write a number in sort of positional notation form or decimal form to get it to the right number of sig figs. So you can use significant figures to do that. Probably more importantly, what we talked about was how to use our calculators, right? So when we do punch our numbers in scientific notation in our calculators, we want to make sure that we are using our EE button, again, our EXP button, or as we talked about, if you have that kind of times 10 to the n with the will, you want to make sure you're actually using the dedicated exponent button to do so. Otherwise, you will find your answers usually pretty far off from what they should be. Also want to make sure you use the proper negative button, not the subtract button, which again on most calculators sort of look like one of those two buttons. So as we talked about, if you do like a 1.25 times 10 to the minus 4, we're going to hit 1.25, going to hit our exponent button, going to do our negative button, and then we're going to do 4. Remember that when you do hit the exponent button, that represents the times 10 part of the number, which again means you do not need to do any type of multiplication number button or anything like that. You just want to kind of punch it in there. We finished up sort of talking about how to take measurements. And remember that when you do take measurements, there is always some type of uncertainty associated with that measurement. And remember that if you take a look at something like a ruler like we looked at the other day, we got 1 and 2. Whenever you look at any scale on a piece of equipment that you're going to use to take a measurement, you always want to figure out, as we talked about, basically what the large markings represent and what the small markings represent. And remember that the large markings typically are the ones that do have actual numbers sort of on them. It is possible, by the way, that the large markings are also the small markings in some cases. You just maybe just have only one set of markings on there, so they can be the same. In this case, again, this is 1 centimeter. We do want to figure out how many of the little guys there are between them. So remember, we always start counting after the last large marking, and we keep counting. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We stop counting at the next large marking. So there are 10 small markings between our 1 centimeter. That means that each of those small markings, once again, is the 0.1 centimeter. Now, remember that we always want to take a reading to the proper numbers. So again, let's just say that our guy was like in this area here. This would be 1.1, 1.2, 1.3, 1.4, and this would be 1.5. So I am at least 1.4, and we would want to record both of those numbers. And as we talked about, those are sometimes referred to as all the certain numbers, the ones that no matter who takes a look at it, everybody should agree that they are those numbers. And those are our certain numbers. But it is not exactly there. And again, that is where the estimate or the estimation or uncertainty comes in. So if I just kind of draw this really badly down there, we're going to go, it's not exactly at 1.5. It's maybe right before it. So maybe we do like an 8 here in a centimeter. That is our first uncertain number. And this would be the proper way to record this. Remember that when we do take a measurement, especially in lab, we do want to include the uncertainty in the measurement. And the way that you can figure out the uncertainty is if you know what the smallest markings represent, all you have to take the smallest markings and divide it by 2. And that will essentially tell you how far you should take the reading to. So again, like we saw yesterday, if I had 0.1 centimeters, I divide it by 2, I get 0.05 centimeters. And that is where the plus or minus 0.05 centimeters come to. We take the reading to 2 decimal places, just like we got there when we divided by 2. So if you are unsure, like we talked about last time, how far you should take the reading to, but you are really sure what the smallest markings represent, just simply divide it by 2, and however far that goes to is how far the actual reading should be taken. Any questions on the stuff we talked about yesterday there? All right, so let's try one more here. I don't think we did this one. So why don't you take a look? We'll zoom it up here. This is, again, another burette here. It's going to come out the bottom. So take a reading of what it should be based on that scale, and we'll see. All right, so let's take a look. And just for the scaling purpose of it, I am going to kind of go below where it's at just so we can see things and not mess up the marking there. So I'm just going to look between here and here. And those are our big markings. And that's 30 and that is 40. So our large markings in this case should be 10 milliliters. Remember that this, again, is a burette, which means it's coming out the bottom. So again, the scale increases in this case as you go down. So sometimes you want to make sure you understand which way the scale is going. So as we come this way, it is actually increasing. And if we take a look at each of the smallest markings between that, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 small markings. So again, if I do 10, each of my small markings in this case is going to be 1 milliliter. So for example, here, this first marking would be 31, right? Next one would be 32, and so forth as you continue down. Now, once again, at this point, if you're really confident about the small marking, I automatically could just figure out how far I should take the reading to. I could take this guy, right, divided by 2, and that's going to give me plus or minus 0.5 milliliters. That automatically tells me that when I take my reading, I should go to how many decimal places here? I should go to 1 decimal place, right? So let's figure out where we're at. This is a meniscus, and kind of right there. And I believe that is the first marking. I think that's the second, third, fourth, fifth. So it looks like it's right on that second marking, which means each of the small markings are 1. So the second marking would be 22 in this case, right? And in this case, though, I should record 22, 22.0, 22.00. Which one should I record? 22.0. Remember that we have the ability on this scale to go to the first decimal place, and we do need to do that because if we do not, we have now just cheated ourselves out of some significant figures, right? So again, if we just recorded 22, this would be 2 significant figures, which means the uncertain number would be this 2. And what we're really saying in this case is, I think it's 22, but maybe it's 23, maybe it's 21. That again is a fairly big spread of difference, which is not what we really have going on here. So we do need to keep this because now this has how many significant figures? This has 3 significant figures, right? As our uncertain number is now here where it should be. And what we're really saying with this measurement is 22.0 milliliters, but maybe it's 22.1, maybe it's 21.9. That is telling us, I think we're like in this area right about there, which is exactly what we see here. So as we talked about last time, we do want to make sure that even if we get exactly on a line or something like that, we do not want to shortchange the significant figures. Otherwise, you are making your measurement a lot worse than it should be based on the equipment that you're using. To fully complete this, we would do something obviously as 22.0 milliliters plus or minus 0.5 milliliters in this case. Any questions on that measurement there? Let's see if that was actually an option. It actually was, I think, actually. There we go. It's actually D, it looks like. It's actually on there. Any questions on how to take a proper measurement? Yeah. All right, so now that we understand measurements is sort of where significant figures come from, and there is a degree of uncertainty with it, we're going to talk about the rules for just counting significant figures in general. So let's talk about the rules for significant figures and how we go about sort of counting whether or not something is going to be considered a significant figure or not. So the first rule is any non-zero number is always going to be significant. So the deal is this: if we have something like we see here, 1, 2, 5, 9, when we are looking to count significant figures, we always start left to right, and we always start counting as soon as we hit the first non-zero. So you do not start counting significant figures until you hit a non-zero number, which obviously in this case is the very first number is going to be a non-zero. So we would start counting. So 1, 2, 3, and 4. So this guy, all of those would be significant figures. That would mean in this particular case, our uncertain digit is which one? It is the 9. Yeah. That is the last significant figure. That would be our uncertain, our estimated digit in this case. Now, zeros are the things that sometimes give people a hard time in terms of significant figures. So there's really 3 types of zeros that we come across. The first type of zero is what's known as a leading zero, and they are not significant. So a leading zero is all the zeros that come before you hit the very first non-zero. So again, going left to right here, these are all zeros. I am not start counting. I am not going to start counting until I hit the very first non-zero. And in this case, that's a 4, which is obviously significant. A 2 is also a non-zero, which is significant. And a 3 is a non-zero number, so it's significant. So all 3 of these guys would be significant figures. And this particular guy here would have 3 significant figures. If we take a look at this one here, again, starting left to right, we're not going to start counting until we hit the 4, which is our very first non-zero. We are then going to count the 9 because it also is a non-zero. So these 2 right here are the 2 significant figures that we have going on in that particular number. Any questions on that one there? Now, the next type of zero is what is referred to as a captive zero, a trapped zero. I think I saw something the other day, a sandwich zero, whatever you want to call it. But these are zeros that are basically trapped between 2 non-zero numbers. So these are zeros that are trapped between 2 non-zero numbers. These are going to be significant. So as we see there, 5.004, we are going to start counting our significant figures here at the 5. These 2 zeros are trapped between these non-zero numbers, so they're going to be significant. So 1 and 2 more, and 1 more at the end. That gives us our 4 significant figures in this case. The uncertain digit being, in this case, the 4 at the end. Any questions on that there? Now, the last type of zero is really the one that gives people the most difficult time, and that is the trailing zeros. And these are the zeros that come at the end of a number. And when you have a trailing zero at the end, it may or may not be significant. So what determines whether or not it is a significant zero at the end or not is this: a decimal point. So if there is an actual decimal point written in the number, not one that you go, I think there should be a decimal point there. It actually has to be written in the number. If there is a decimal point written anywhere in that number, all the zeros at the end are significant. So if you have a decimal point anywhere in the number, going to be significant. So anywhere in the number, it's going to be a significant zero at the end. So as you can see here, if we wrote 600 like this, this would have how many significant figures if this was like a measurement? It would have only one significant figure. There is no decimal point written in this number, and that means those two zeros at the end are not significant. This would be one significant figure. By the way, the uncertain number in this case is which number? The uncertain number in this case is it is not actually in this case. It has just one significant figure, and that significant figure is which number? 6. And that is also our uncertain number. So in this particular case, the uncertain number in this case is the 6. And that's what I was saying yesterday when I said it will not always be, for example, the estimated digit. It may not always be the last number that's written, but it should be the last significant figure that is written. So in this case, since we only have one, it is the 600. And that's why this measurement here is not the greatest, because basically what we're saying is, I think it's 600, but maybe it's 700, or maybe it's like 500. That's a pretty big range of not the greatest measurement made by anybody, right? Now, if I take the same 600 and I put myself a decimal point there, how many significant figures does it have now? 1, 2, or 3. Hopefully not 4, because there's not 4 numbers, right? How many? It does have 3, right? So there is a decimal point here, and that's going to make these guys significant. We are going to start counting here at the 6, and because of that decimal point, this would be 3 significant figures. And with that guy, what we're saying is, I think is 600, but maybe it's like 601, or hey, maybe it's like 599, right? So the estimate is over there in the ones place, right? Rather than the other one where it's in the hundred place, right? A lot more room for error. Any questions on that there? So if I had this number here, that was some type of measurement, 0.0042500321000, and I'm going to go grams. I'm not sure how you make that measurement. But how many significant figures would this number have? All right, let's take a look, because I don't know. I was just writing. So let's start here. Are these zeros significant? They are not significant. Now, some people will say, but don't those zeros come after the decimal point? And the answer is they do. But the problem here is I have not started counting yet, because I have not hit the very first non-zero, right? So I'm not counting my significant figures until I hit the very first non-zero, which is there. And that is my very first non-zero. So that means all those zeros are technically leading zeros, which are not significant. Now I'm going to count. So that's a non-zero. That's significant. That's significant. That's significant. These zeros seem to be trapped. So that's going to make them significant. That's a non-zero, significant, non-zero, significant, non-zero. Now, what about these zeros at the end? Are they significant? The zeros at the end here are significant, because way over here, there is a decimal point written. The decimal point does not need to be like right next to the zeros. Again, just needs to be anywhere in that number. So I totally lost track. Let me recount here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This would have 10 significant figures, with the very last zero in this case being the uncertain one. How you would do that measurement, I'm not really quite sure, but I just made up one there. Any questions on that there? That should have all your zeros in one spot right there. Questions? No? Yeah. All right, now that I wrote over this, let's talk about another type of number that we commonly come across, and that is what is referred to as an exact number. Now, when we do take a measurement, that is what is obviously referred to as a measured number. And measured numbers have uncertainty, and they have specific numbers of significant figures associated with them. So if you take a measurement, there should be a specific number of significant figures that you should give for your measurement based on the equipment you're using. With an exact number, it is basically one of two things that you come across. An exact number is something that you normally would not do any type of experiment or measurement for. So, for example, if I had this pen on the bench here, or these couple of pens on the bench, I am not going to do some type of experiment to figure out how many I have. I'm simply just going to count, right, how many there are. So an exact number is something that you get when you count something. The classic textbook example is apples in a barrel. Basically, you just got apples in like a little barrel and you count how many you got, you count how many there is. The other common way that we have an exact number is a definition or an equality. And those are, again, two things that equal the same amount of something, but are on different units. Like 100 pennies is $1, right? 12 inches is a foot. These are definitions that are considered exact numbers. Now, what is the deal with exact numbers? The deal with exact numbers are because they're counted, because they come from definitions, they technically could have as many significant figures as you like, right? They have basically an unlimited number of significant figures. What that means is when we talk about calculations and given our answer to the proper number of significant figures, if you come across something that is considered an exact number, the good news is you do not have to worry about that number in your calculation and like, should I determine how many significant figures that will give me based off of that number? We sort of ignore exact numbers in their contribution to significant figures in a calculation. Now, here are some exact numbers, and definitely here at this school, they like you to know everything, right? So I'll just put a big no on this, yeah. So these are some very common sort of equalities that are definitely exact numbers. The 1 inch is equal to 2.54 centimeters, I think we saw yesterday. 1 pound is 453.6 grams. 1 foot is equal to 12 inches. 1 yard is 3 feet, and 1 mile, 1.609 kilometers. Now, as we talked about in terms of units, there's really two types of units, right, that we talked about. There are US units or English units, and there are basically metric units. So if you remember, pretty much everybody else uses the metric system. We roll with the US and English system. So when you come across something, do you have a question? Yeah, we'll see some more as we go through the chapter in terms of what you need to know. Yeah, but that's a good one. It does pop up a lot, actually. Yeah. So if you come across an equality that is a English to English sort of equality, like 12 inches is 1 foot, that is definitely going to be considered an exact sort of number. If you come across like a metric conversion, like there's 1,000 grams and a kilogram, like a metric to metric conversion, that is going to be usually considered an exact number. You only really has to worry about if you're using like a conversion that kind of crosses over between an English unit to a metric unit, like maybe quarts to milliliters or something like that, or that type of conversion. And in those cases, those are typically not considered an exact number, and you do have to kind of look at the significant figures in that case. But a couple of exceptions, obviously the inch to centimeters is considered an exact number, so you don't have to worry about it. The grams and pounds one's considered an exact number. So again, you could consider those guys exact numbers. Any questions on that? So let's just take a look at these here and see what we end up with. So taking a look at these examples, once again, starting left to right, we are not going to start counting until we hit the 3. And obviously, this is now a trap 0, and that 4, and all those guys with the arrows are going to be significant, and that would be our 3 significant figures in this case. Here again, we have a number that is written in scientific notation. So all the numbers before the times 10 part, again, are going to be significant, and that is 4 significant figures. Here, starting left to right, we're going to start counting at the 1. That is a non-zero and a non-zero. So all 3 of those would be significant. Here, this is going to be significant. This is a 0 at the end. And again, there is no decimal point written. So we do not assume that it is there when we're doing significant figures. We do assume the decimal point is there when we're doing like scientific notation, but for significant figures, we don't assume it. And that's obviously just 1, which would be this guy. And that again would be our uncertain number in that case, would be the 1. Here coming this way, 9 is where we start counting. That is a trap 0, that is a 2, and that 0 at the end is significant because there again is a decimal point written here. So once again, these guys here are going to be our 4 significant figures. Any questions on that there? All right. Let's talk a little bit about rounding rules, and normal rounding rules apply. So if you are kind of less than 5, we basically just drop the numbers. If you are more than 5, we usually round up, and we need to look at the number that comes after the number we want to round to. You don't want to do any kind of weird rounding for sure. So if I had 13,333 and I wanted 2 significant figures, what should my answer be? Is it 13? Is it 13,000? Is there a difference? Let's take a look at this one. This one has how many significant figures? That's the way I wrote it. That has 2 significant figures in this case, right? So that's good. How about this one? This one has 2 significant figures as well. These are significant. Zeros at the end are not significant. There's no decimal. So they both have 2 significant figures, so that checks that box, right? Do they represent the same amount of everything? They definitely don't. If you don't see that, let me just give you this example. Let's just say hypothetically I owed you $13,333. And I go, I'm going to give you 2 significant figures. Here's 13 bucks. Probably not going to make it out of the room. Maybe you guys look nice, and maybe I'll get out of the room with that. But you're not going to be really happy with me because there's a very big difference in the meaning of $13 and $13,000, right? So although this guy on the left has the right number of significant figures, by rounding sort of extremely here, we have changed the meaning of that value, and that's not what we want to do. Now, 13,000 is pretty much the same sort of value as 13,333. Maybe get like a $333 teacher discount, not too bad. And, it basically means the same thing. So you never want to round extremely that you change the meaning of the number because it doesn't mean the same thing, obviously, in that case. And it happens a lot when people are really fixed in on, like, I want to give the right sig figs, that's all they kind of focus in on is, I need 2. So they just like lop off all the rest of the numbers and stuff like that. And they're left with a number that has the right number of significant figures, but is not the right value anymore because you changed what it means. So you want to be really careful when you round that you never change the meaning of the number and that you round correctly. Again, that may mean you got to turn some things into zeros and not include decimal places. It may mean, for example, I could have also done 1.3 times 10 to the 1, 2, 3, 4. And that would have had also 2 significant figures, right? If I wrote 1.30 times 10 to the 4, would that have 2 significant figures? That would not, because now that has 3, right? So that wouldn't have been good in this case either. So you do want to be careful with the rounding. You also want to be careful with, if you do write in scientific notation, how many zeros maybe you put there or no zeros, as it does affect the number of significant figures. Any questions on any of that there? All right, we're going to lay it up there.